Hey guys, so today I'll be covering something that will be really quick. I just want to go over what titration is again. So what you guys need to know is what is titration, right? So this is an analysis of vinegar using a standard solution of sodium hydroxide. And immediately vinegar it should come immediate to you that is acetic acid. So we're testing a acid using sodium hydroxide NaOH, a base, right? It releases hydroxide ions. But as we know, there are multiple definitions for a base. We can talk about the Arrhenius ones, from the very basic ones, which was, did it taste sour? Did it taste soapy? From then it became, does it release hydrogen and does it release OH minus? But, simple refutation would be ammonia, in which case now we talk about, is it a hydrogen donor or a hydrogen um, donor or acceptor, right? Receptor. Okay, does it donate or does it accept the hydrogen? And nowadays we typically either use that one, which is the Bronson-Lowry definition, or we would use the Lewis definition, which is simply does it accept or donate a pair of electrons, right? So, yep, just be aware of what a titrant is. Let me find my notes here. Oh, this is also very useful for you. Understand that a strong acid will completely disassociate to become what? Its constituent parts, right? So HCl would become H plus and Cl minus. So it strongly dissociates because it's a strong acid because it strongly dissociates. But also, this is very important, a strong acid has a weak conjugate base, okay? So Cl minus, therefore, is very weak as a base, okay? So you can just be aware of that. Other than that, so we talked about dissociation. Therefore, what is acetic acid? Is H2COOH, I think H2COOH, which will become H2COO minus plus H plus, right? So if this is a weak acid, this would be, that's right, a strong base. Okay, that's just something useful to know. Other than that, let's see. What is... Okay, so typically for this one, let's see, what did we use as a identifier? We used phenolphthalein indicator, and that would be very important as well. What is an indicator, right? It's basically just acids and bases. It's a solution of either an acid or a base. They're all acids or bases, but they're able to have a physical change at a certain pH. So I'll give you guys a few right now. Phenolphthalein, for example, is very common when it's one that turns pink. So phenolphthalein, it turns at around 8 to 10. I think the real number is like 8.2 to 10. That's okay. We have bromo thymol blue. So bromo thymol blue, I'll just type it as BB. That'll be 6 to 8. And final methyl red, so MR, it changes at 4 to 6 pH. So you have typically, when in your HSC or whatever curricula you do, they might give you something to do with pH, and it will be worthy to memorize these. Just know that phenolphthalein is the one that turns pink, and it's around 8 to 10. You might want to do bromothymol blue around 6 to 8, or methyl red at 4 to 6. But what it depends on is your equivalence point, right? So we'll talk about that in a bit. Just keep in mind what those are first. And that was page 1. Sorry, these pages are a bit messed up, so I'm going to go through. So, understand that we need a standard solution, one that we know the concentration of, to test the concentration of the constituent, to test for the analyte, okay? So what we're analyzing. So for example, in this one, it would be the concentration of acetic acid or vinegar, and we're going to determine that through a standard solution of sodium hydroxide. Gradio. So standardizing sodium hydroxide, and then we determine that. So that's titration summarized. Beautio. And yep, we have 5 trials. Once again, why? Because we want to get something that is very accurate, right? We want reliability, consistency, and it can help us determine whether or not our testing is consistent. Okay, calculate the concentration of potassium phthalate solution used. Calculate the... Bada boom, bada boom. Oops, here. I think this is the next page. Average Okay, calculate the moles. Done, done, done. Okay, so let's talk about this. Compare your answer with other groups. Don't worry about that. I can't do that with you. Calculate a percentage acidity. I don't have any results for that. That's fine. What I really wanted to do with you guys was this kind of stuff, right? So we're going to do the okay. Let's just start to do some questions then. Bam, bam, bam. So we have oxalic acid. Ignore the working out. I was doing it with my student. Okay, we have just ignore all of this. Don't worry about it. Don't worry about this. Don't worry about this. I'm going to quickly go over it. Okay, we have 12 grams of. So one thing is first is we really want to be able to write out the equation. I'd say the first step is equation. Okay, so actually understand what's going on. You know, you can give it a balance. That'll be very useful if we want to use molar ratios. And then 3, find out what we're actually doing. So what we do, WWD, whatever that means. Okay, so we have oxalic acid, H2C2O4. Okay, and we dissolve it in water, H2O, to give, what does it do? Okay, we dissolve it in water, and what that means is if it's an acid, if this is an acid and this is water, water is something we call amphoteric. It can act as a base or a acid. So in this case, if it's reacting with the acid, what would it make? So this would make HC2O4, right? And that was an acid, now it's a base, so it's minus, and plus, so if that was a base, water now accepts the hydrogen ion as H3O plus. One thing is this, okay, know this, and this is something that trumped me as a student, okay? I was too naive. That was very useful, okay? Okay, and here we have this. Right, is it balanced? Let's double check. Carbon's balanced, Gucci. Hydrogens, 4, H3O4, beautiful. Oxygens, 5 and 5, beautiful. So it's balanced. And finally, what are we actually doing? We have 12 grams of this. I like to write it right under it so we can, you know, actually match it up. And grams, units is very important. This is mass. Great. Now we have, what else do we have? We have dissolved in water to give 500 ml of the solution. Alright, so we have volume is equal to 500 mils, right? And what does it want? Calculate the molarity. Oh, great. Okay, so that's mils. That's why I made you guys do volume. But remember, we need to calculate it as 0.5 because volume is in liters, right? Well, not volume is in liters, but now when we calculate the molarity, which is m, right? Or we also know it is moles per liter, right? So we have mass, we have volume. Now we want to calculate what? We want to calculate concentration or the molarity, which is N over V. Dissolve enough of water, calculate molarity of the solution. Okay. Yeah, quite simply we find the molar mass, which I just cheeky saw in my thing is, so what's a moles? Moles is mass over molar mass. We have 12 grams and it's over 90, around 90, we'll use 90, right? So that would be moles, right? Over volume, 500 mils, so we write 0.5 liters, and we get a cheeky answer of, I'm just going to peek at my own answer, I think it's 0.26, so, oops, so 0.266 molarity, right, which is also moles per liter. Sweet. And was that all a wonder from us? Calculate the molarity. So great. Now you just go through the question again. Did we answer it? Yes, we did. Beautiful. I'm going to rub this out in case it becomes distracting. Next one. Okay, we have a titration of. I'm just gonna. Oops, can I rub? Okay, don't worry about this then. Okay, we have a titration of sodium hydroxide pipetted into a conical flask of sulfuric acid. An indicator was changed. Okay, so first things first, as we said before, what do we want to do? We want to find the actual equation of the solution. So NaOH plus sulfuric acid, H2SO4. What does it make? Okay, we have base, we have acid. Now we'll just make HSO4 minus. Right. Okay, so we have acid and base. What does it make? It makes a salt and water, right? So, oops, that was wrong. We have sodium hydroxide and this, therefore it would make Na2SO4 plus H2O. Gradio. and this would be a salt, and this would be water. Great. So you know this from introductory chem that acids and bases make salt and water. Now, what do we want to do? Is it balanced? Yeah, it's balanced. I'm just doing this from memory because, wait a minute, where's the two? There's two sodiums, so clearly my memory isn't that good. Wait, let me actually double check this if it's balanced. Okay, sodium is balanced, sulfate is balanced, water is balanced, oxygen is 5 and 5. Okay, great. So now it's balanced. Sorry about that. Okay, never be too confident in yourself, but don't be unconfident in yourself. Okay, so we have 25 mils of sodium hydroxide, so volume is 0.025 liters. You can get into the habit of converting it to liters instantly. Okay, we put that into a conical flask, and we have what? Of sulfuric acid, we have moles per liter. That is what? Concentration. I'll write it in this one. So concentration is equal to, oops, that is terrible. Concentration is equal to 0.1. That's terrible as well. Jesus. Okay, pen. Okay, so concentration is equal to 0.1 moles per liter, right? And what else? An indicator was changed when 22 mils of the acid has been added. So once again, volume is equal to 0.022 liters. Now what does it want? Write a balanced equation. Okay, so we did that. Beautiful. Calculate the number of moles of sulfuric acid. Very easy. So we have this, right? Sulfuric acid. We have CV. Now we want N. So C is equal to N over V. So N is equal to C times V. We simply multiply these two together. And so 0.1, which is 1 over 10, times by this. You simply move the decimal point back by 1, right? And you get this. This is moles. Okay, so I don't know what my student wrote here, but that should be moles, right? Because it, oh wait, no, that's volume. Don't know what she was doing here. Okay, so that is moles of sulfuric acid, right? Beautiful. Now calculate the number of moles of NaOH reacted. So this is something cheeky, right? We noted molar balance. There's actually a 1, there's a 2. I taught you guys this before. It's not very accurate, but if you have a balanced equation, you can simply do this. If we have 1 mole of sulfuric acid reacts with 2 units of sodium hydroxide, we just multiply the moles, right? Because it has to be 1 unit of this multiplies with 2 units of sodium hydroxide. We can just say is equal to, I'll write it out for you guys, OH should equal to 2 times H2SO4 moles, right? So we have N of NaOH would equal to 0.0044 moles. Sweet. Now we want molarity. Remember, molarity is moles per liter. So that's concentration, right? And we need moles over volume, which is 0.0044 moles. We're taking that from before over volume, which is, what is the total volume now? Okay, we have 25 mils of sodium hydroxide. And what else do we have? We have 22 mils of the acid. In total, the volume would be 47 mils, or we want to rewrite that into liters, so we put 0.047 liters. And now, you get something, but I don't know what it is because I don't have a calculator. Always have a calculator nearby. So that's that. Beautiful. So I'll write it ANS, just so it doesn't look empty. What indicator is used in this saturation and why? Okay, so here we want to look at which one is stronger. Is sodium hydroxide stronger or is sulfuric acid stronger, right? We talked about this before. Because sodium hydroxide or sulfuric acid going to dissociate into more things, right? So this is actually a really good one. We can talk about this. NaOH would become H2SO4 would become, we know that it will become HSO4 minus plus H plus, right? And Na minus plus OH, Na plus OH minus. So which one looks more dissociated to you? This one, right? Sodium hydroxide. And this one is not as dissociated. I always like to talk about it like this, sodium hydroxide is a clingy couple. It's a toxic relationship, right? It only has sodium only has hydroxide, right? And HSO4 it's a player. You know, it has many holes. So when one of the holes goes away, it's not as concerned. Whereas sodium, you know, he's like, you my only one. So okay, sorry about this, guys, but you know, that's how it works. It's a stronger acid. It's a stronger base because it dissociates stronger. Therefore, do you think if it's a strong base and it's not a weak acid, sulfuric acid, but let's just say relatively speaking, it's a weak acid, what would happen? Strong base and a weak acid. Is it going to be above 7 or below 7? Below 7 meaning it's more acidic. Above 7 meaning it's more basic. Above 7, right? So we can do something that is like phenolphthalein, right? Phenolphthalein would work because we know that it uses 8 to 10 pH. That is when it changes color, right? Beautiful. We covered that. So sulfuric acid, I'm going to cover these two quickly as well, and then I'm going to cover the rest in another video. But these are the basic questions you get in a titration track. So we have sulfuric acid. Okay, I'll do it properly, like I'm actually solving a question and I'm talking my exams. Decided to determine the concentration, so we want the concentration of this acid, taking 2 mils and titrating at 1.16 molarities of sodium hydroxide. 17.1 mils was needed to reach an equivalence point. Okay, calculate the molarity of the sulfuric acid. So what we want is sulfuric acid reacting with sodium hydroxide. Same again, H2SO4 plus NaOH, we know that will be 2, would react to make Na2SO4 plus H2O. Great. And we know that is balanced because we did that just then. Once again, how would we do this? Concentration of this acid. We want to determine the concentration of the acid, so it's X. Okay. By taking 2 mils of it and titrating, so volume is 0.002 liters, titrating it with sodium hydroxide at 1.16 molars per liter, right? So that's standard concentration, so we'll do M for molars. Okay, molarity. Then we needed how much? We needed 17.1 mils. 17.1 mils, which is, 7.1 liters, right? 17.1 mils is 0.0171 liters to reach the equivalence point. Now, what do you know? If you just simply look at this, it sort of flows, right? We have C, we have V, now we want N. C is equal to N over V, so N is equal to C times V, right? So 17.1 times by 0.071 times by 1.16, and we should have our answer. I'm actually going to solve this one because I need to get the intermediate answers. Otherwise, I can't actually finish the question. 0.0171 times 1.16, and we get, I'm just going to put it into its sig figs, 1.98 times 10 to the negative 2, right? And this is moles, okay? Now we have moles of sodium hydroxide. We want to find the molarity of this. So I'm going to change color quickly. What we can do is quickly find the moles of H2SO4, and now I'm going to give you 10 seconds to think how you do that. 10 seconds, but you need to pause the video because I'm going to continue. Okay? Simply using the molar ratios, right? If there's 2 of these required to make 1 of these, we divide it by 2. Similar to before, and that would make 9.92 times 10 to the negative 3. Okay, and now simply we want to find the C. C is equal to N over V. We divide this by this. Okay, divided by 0.002, and you should get something like 0.002, something like, oops, divided by 0.002, 4.95. So we'll say it's equal to 5. And concentration units is m's, right? Or moles per liter. So that's very quick. One more. I'm going to do one more. It's sold commercially as solid lye. This one is something you'd get. So I want you to try this yourself first, but I'm going to continue. Okay, we have NaOH, sodium hydroxide, right? NaOH, and it reacts with was required. Okay, so it's reacting with HCl. Okay, so we have NaCl plus H2O, acid and base, salt, and water. Great, and it's sold as solid lye. So therefore, sodium hydroxide exists inside solid lye, we have 0.308 gram sample of lye required, 22.5 mils of sodium hydroxide. So we'll just do that. Volume is equal to 0.0225. Is that right? So this would be hundreds, tens. Yep. And this would be liters of here of hydrochloric acid. We have concentration is 0.25 molarities, so that's accurate. Now we just want N, so C is equal to N over V, so N is equal to C times V, right? Great. 0.25 times 0.0225. And the answer to that is 5.63 times 10 to the negative 3, right? What else do we have? We have, okay, so if we have moles of hydrochloric acid, we technically already have moles of NaOH, which is 5.63 times 10 to the negative 3. Okay, we have, okay, so we have moles of this, and we have this, okay, of lye. If we want the mass, we want to compare the masses, we also have the molar mass of sodium hydroxide, right? Okay, 39.997. I'm just going to do it accurately. 39.99, so mass is, oh, by the way, this is grams per mole, okay? This is mole, therefore, when you multiply them together, this cancels out and you get grams, right? So it works out, chemistry is not a lie, okay? 39.99 times by 5.63 is equal to 225.14, but this is times by 10 to the negative 3, so the actual answer would be 2.25 times 10 to the negative, okay? Negative what? Negative, is it going to be up or down? It's going to be negative, Jesus, I'm getting confused by my own maths. Okay, ignore this, I'm a bit tired. Okay, so we'll use this, and we're going to, so this is the mass, right? Okay, and we want to find the percentage by mass of sodium hydroxide in lye. So lye has 0.308 grams, and we want sodium hydroxide inside this, which is, so this is negative 3. Okay, I'm just going to do it properly. So negative 1, 2, 3. Okay, so, okay, I'm solved. No, 22.514. And that would be percentage by mass of sodium hydroxide inside lye, right? So that'll be 0.22514 divided by 0.368, and you get something like 61%, okay? Oh, no, it will be like 0.61, but you need to multiply it by 100. You guys know this to get a percentage, and that will be 61% of sodium hydroxide by mass inside lye. Okay, I'm going to cover some other stuff. Let me know in the comments if you want me to do something cheeky quickly. Right. Okay, so weak acid and its conjugate base, natural buffering solution in the lake is a result of dissolution of what in the air. It could be carbon dioxide becoming carbonic acid. I'm not too sure other half of buffer solution containing sodium acetate would be. So sodium acetate is Na, and acetate, like acetic acid, is HCOOH. It would be just NaHCOO, right? So this is acid, this is base, right? Something like that, very simple. Carbon dioxide would dissolve in blood or water to produce carbonic acid. The other half of the buffer system is the common ion. The OH minus ions increase in the blood. H2CO3 reacts to what the OH ion concentration reacts to. Oh, it will be decreased, right? So, the buffer solutions, what is a buffer? It is basically acids and bases, but they resist change. So we have H, A, and we have A minus, right? If we add acid inside, what would happen? It'd react with this and just make water and salt, right? And if you add base, it would react with this, and this would just become H, and this would become water, but you have a remainder A minus, and it would just become a base, right? It's a weak base though. So that's essentially how buffers work. It balances and resists change. Yeah. If you want me to quickly go over these next time, I have a few more pages here. I can. Just let me know in the comments which one would be relevant for your studies. And yeah, thanks.